Start recording. Welcome everyone, and today we are starting our third session in our workshop, and we are really happy to have Andrej Risteski be our speaker today. So Andrej got his PhD from Princeton and now is a professor at CMU, and he works on this really interesting interface of machine learning and statistics. In particular, he spends a lot of time thinking about representational learning and generative models, and today he will talk about, well, especially about the latter. So without further ado, Andrej, please go ahead.
Thanks, Alexander. So I'll talk today about a couple of kind of vignettes in some algorithmic and representational kind of questions around generative models, and the kind of link between all of them is going to be a kind of like natural randomized process called Langevin diffusion. And I kind of added this very last minute after going to Rishi's talk yesterday, so I couldn't resist. So the alternate title is Langevin is all you need. I guess hopefully you get the joke. All right, so let me, I guess, set the stage a little bit, and let's see if my slides will advance. Like the context is basically, I'll talk a little bit about some questions around unsupervised learning, and the idea here is loosely that you want to do some kind of learning and you don't have labels available. What can you hope to do when you have no labels? Well, there's kind of classical things like just maybe understand some structure in the data. So this could be some kind of latent information, could be some kind of correlations or causal structures. So maybe you want to kind of learn the causal structure between diseases and the symptoms they cause. Or it could be some kind of more modern applications. So basically things like learning how to generate new samples, maybe even while doing some kind of complex conditioning. So I'm sure some of you have seen kind of in the media these sort of results that, for instance, from this system DALL-E from OpenAI, where you can kind of generate these pretty impressive looking pictures just by kind of giving the model some description of what the picture is supposed to be, and or like extract some kind of complicated features and do domain adaptation. So that would be things like taking pictures of kind of regular humans and making them look like cartoon avatars or something. So one of the success stories in this kind of area have been generative models, and the idea is sort of relatively simple. So the idea is to kind of fit some kind of probabilistic model that's trying to describe how the data was generated. And like the usual, I guess, like way to motivate these things is kind of by Feynman's adage, what I cannot create, I do not understand. So how does it help with some of the tasks that I described on the previous slide? Well, ideally, if you have a rich enough model, you can hope that the structure of the model somehow reveals some structure in your data. And, of course, if you have a flexible enough model, you can also hope that you can learn some new structure. If you want to draw samples from the model, that's kind of a way to generate new samples. So that helps with kind of like the sample generation examples that I showed you. And of course, if you have like a, nice enough choice of a model, you can maybe do some kind of judicious conditioning. So you can do some kind of like, more complicated kind of steered generation instead of just sort of generating samples. So this was maybe like the most famous breakthrough in this area were GANs. I'm sure by now all of you have heard of GANs. So they were kind of pronounced one of the top 10 breakthrough technologies in 2018. They were probably like the original model that was capable of creating these photorealistic images and videos. So, if you have sort of certainly you've seen these kind of like deepfake style videos where you take kind of like a scene from Superman and you kind of in-paint Nicolas Cage into it, because why wouldn't you? And a lot of these sort of domain kind of adaptation tools, like maybe taking pictures and making them look like they were painted by Van Gogh, are also kind of based on this technology. So this was 2018, and actually the Goodfellow paper on GANs was 2014, which in kind of deep learning, I guess like timeline is forever ago. So what's been happening since? So what's been happening since is that really there's been this kind of proliferation of generative models of all sorts of different types. So there've been kind of many different variants that people have kind of either come up with or sort of like, perfected some past variants of them. So just to kind of give you a sense, there's things like variational autoencoders, which are basically a neurally parameterized Bayesian network. GANs I already mentioned. Normalizing flows have been quite popular, and I'll talk about them a little bit today. So these are some kind of like, push forward forwards of simple distributions like a Gaussian, again, neurally parameterized and trained using maximum likelihood. Energy-based models, so basically these are models that are somehow parameterized up to some kind of partition function and then trained either using maximum likelihood or something called score matching. And actually there's lots of others. The sense I'm trying to give you that there's just been like a lot of different variants, and so kind of what should we make of this as, I guess, like this is Fox, right? So as theory leaning folks, like what should we make of this? Well, one of the kind of main, I guess, questions, and this is both a kind of theoretical and empirical question, is that it's not sort of super clear what are the relative pros and cons for these different models. And maybe most importantly, it's not actually clear what exactly the the performance improvement, if there is one, like what exactly it's due to. So by that I mean, like, it's kind of unclear whether there's something about the model that's better. Maybe the lab just had more compute and could scale up the model more, or let's be honest, maybe the grad student who was working on the project just was more persistent engineer and just managed to make it work better. And so somehow, like, there's something unsatisfying here, which is that it's kind of unclear in which settings what models you should use, and whether one type kind of dominates another. And of course, if you want to kind of answer this maybe a little bit more mathematically, the reason why this is kind of difficult is that there's sort of difficult things that you have to understand. So when you say advantage, like what kind of advantage do you mean? Like, is this a representational advantage? So maybe some kind of, types of data can be kind of more compactly represented with one type of model versus another. Is this advantage algorithmic? Like maybe some kind of task with the model, like maybe doing inference or drawing samples, or maybe just like learning, or somehow algorithmically easier. And like, why is it difficult to understand these questions? Well, the reason is that, this is going to heavily depend on the type of data that you're training and using the model for. So basically, this is going to be pretty complicated data. All of these models are usually trained either on, like things like real life images or natural language. And honestly speaking, we just don't have great kind of probabilistic models to try to analyze these, like these kind of questions in. And so that kind of seems to be one of the hurdles. So this is like the kind of very, I guess, ambitious thing that we'd like to understand. Just to manage our expectations, I'll talk about this, but I'll sort of, I'll set my expectations a lot lower. So my goal is to sort of tell you about a couple of pitfalls that people empirically have observed for kind of several of these types of models. And I'll tell you sort of when they can be hoped to be avoided or improved. And as I said, the common thread will be that the way I'm going to do this is like, I'm going to use either as a kind of proof technique or as an algorithmic technique, this Langevin diffusion. So the three vignettes that I'm going to tell you about are the following. So I'll tell you about an algorithmic task, which is sampling from distributions that are multimodal. So those are things that have kind of multiple humps. So like what I'm showing you on the right here. And I'll sort of like mention how you can do this by this kind of randomized process, Langevin diffusion, plus a technique called simulated tempering. Then I'll also tell you about a case for Langevin diffusion can be used as a kind of proof technique. So how you can sort of argue that you can design well-conditioned normalizing flows. That's one of these kind of types of models that I mentioned by sort of simulating an underdamped version of this Langevin diffusion. And then the final vignette will be to tell you how you can kind of control the complexity of posteriors, or as they're often called, encoders, in one of these models called variational autoencoders, again, by sort of like simulating in a neural fashion Langevin diffusion. So I get that there's a little bit of nomenclature here, but don't worry, I'll kind of explain all of this as I'm going through the slides. And maybe I should say, because I didn't say this in the beginning, it's a bit difficult for me to mind the chat or anything else, but if you have a question, just feel free to kind of unmute and stop me, so I don't feel like you need to wait until the end. Okay, so let me tell you about the first vignette. So this is going to be about efficient algorithms for sampling from multimodal distributions using this process called Langevin diffusion. So let me do a little bit of context staging. So I'll give you two examples where the algorithmic task that I'm going to look at kind of appears very naturally. So one is just probably pretty natural for, I guess, like TCS audiences. So it's the kind of this latent variable modeling paradigm, wherein what you do is you assume that the data is somehow simple if you condition or you give me some kind of unobserved latent variables. So how does this kind of manifest? So maybe, you can imagine that I have some kind of modeling assumption on the joint probability of, let's say, diseases and symptoms. The diseases are, of course, latent. You don't get to see what diseases the patient has. And maybe, like you postulate that this distribution factors into, the probability of the diseases and the probability of the symptoms given the diseases. And you imagine that these two kind of factors have some simple parametric form. Then one kind of common task that you want to do with this sort of model is what's kind of generally called inference. And, it's kind of how you would use the model, right? Like suppose that you have a trained model, how are you going to use it? You're going to get a new patient with some symptoms and you want to figure out what's the probability that the patient has a particular, disease or set of diseases given the symptoms. This is nothing but sampling the posterior in this model. What makes this task challenging? Well, by Bayes' rule, this posterior is proportional to the joint probability of the diseases and the symptoms, which, by our, I guess, like, stipulation is going to have some simple form. Of course, as usual, when you have these simple distributions up to a constant of partition, the problem is that this, partition function is some kind of, either combinatorial quantity or some high dimensional integral. So that's kind of where computational hardness sort of creeps in. So that's one kind of like sampling, I guess, example that I want you to have in mind. The other one is maybe more kind of recent. It's sort of these energy-based models, which also I like to call them unnormalized density models, where the idea is that you're going to fit some kind of probabilistic model where the probability is kind of proportional to some exponential of some energy function. So this E theta is usually called some energy function, and you'll train this energy function from data. Well, if you imagine this E theta is, let's say, parameterized by something like a neural net, well, what's one way to train this? Well, if you could write down the maximum likelihood objective, you can just do gradient descent on maximum likelihood. So that's like a very kind of straightforward way to train a model like this. And if you try to figure out what's the gradient of the log probability, and you sort of like explicitly write out this partition function, what you're going to see is that you have a term that looks like the gradient of the log partition function. And if you kind of remember your basic calculus, by chain rule, gradient of log z is 1 over z, grad of z. And then if you explicitly write out the partition function, what you can see is that you can rewrite this quantity as the expectation under your current model, so under p theta, of some simple to calculate thing. So if E theta is a neural net, this is some kind of simple quantity to calculate. So that just means that if I want to do gradient descent, it sure would be nice if I could draw samples from a model P theta that's parameterized in this fashion. And this is not just kind of like a, I don't know, like a invented problem or something. Like actually there's pretty kind of well-performing models that have this form. I'm showing you here like a figure from one of the, I guess, like original papers that propose this way of I guess, parameterizing distribution in generative models by Song and Hermon. And you can see that you can get pretty good samples. And this is a paper from 2019. Actually, versions of these models now are even better at generating samples. Okay. So what's the pitfall for the that I want to kind of address? So the pitfall is multimodality in these distributions. So without a lot of math, just kind of with pictures, here's sort of the problem. So suppose that you have some kind of model that's, like maybe has this kind of energy form, and you want to generate, I don't know, like images that match some descriptions. So maybe, things that match a scientist in a lab coat. And, maybe the model generates the things on the right. So there's sort of a problem here. The problem is that you kind of missed kind of parts or modes of the distribution. So you would imagine that like, a well-trained distribution for scientists would have like, maybe multiple modes here for different kind of like genders, different ethnicities. And if you look at the pictures, they're all kind of, well, I took stock pictures of like, white men in lab coats. So, like this is sort of like a prototypical example of what would happen if you, if kind of like your sample should have missed parts of the distribution. Okay, so to describe mathematically the results, let me give you a kind of an abstraction of these examples that I was talking about. So what I'm going to be interested in is to sample from a distribution, let's say P of X, that's given to me up to a constant of proportionality. So it's proportional to e to the minus f. And maybe the way I have access to this function is, by gradient and value queries, so some kind of like, black box setting. And this should kind of remind you of the usual black box setting for optimization. Just a small remark, this is basically without loss of generality, so I can always just take like f of x to be minus log p of x. Okay, so this is the problem we're going to be looking at. Now, let me describe this kind of like random process that I'm going to be looking at, because I've mentioned it multiple times and I still haven't given you a definition. So if you're not familiar with this, it's actually kind of fairly natural. So it's a kind of random walk, which is sort of like an analog of gradient descent. And maybe the easiest way to introduce it is like, it's basically the limit as you take the step size of 0 of the following random process. So if you're at point xt, first you're going to take a direction kind of opposite of the gradient. So the same way you would do in gradient descent. Difference is you're going to inject a little bit of Gaussian noise with some appropriate scaling. And this turns out like this process has some nice properties. So if you take the, like in some appropriate sense, if you take eta going to 0, what you get is an object called a stochastic differential equation, which is kind of an analog of gradient flow, which I've written here. But again, if you are unfamiliar with this kind of formalism, don't worry about it. It's basically just, some way to say that you're kind of moving a little bit the opposite of the gradient, and then you're ejecting some infinitesimal version of like a Gaussian, which is Brownian motion. The nice thing is that the stationary kind of distribution of this process is the one that we're trying to sample from. So it's this P of x proportional to e to the minus f of x. And the one kind of caveat here is, unlike optimization, the scaling of the function here actually matters. So if you're kind of used to thinking about this black box setting for optimization, typically sort of like the scale of the function doesn't really make the problem easier or harder. Here it does. And the reason is that, I guess what I have on the cartoon here. So if I take a function e to the minus f of x and e to the minus f of x over 10 over 50 over 100, the more I divide by, the kind of flatter the distribution gets. And you can kind of like guess that maybe flatter distributions are easier to sample from. Okay, so extending sort of the parallels with optimization, the same way that you have a dichotomy for kind of optimizing functions, and you know that convex functions are easy to optimize, non-convex things are in general NP hard. Kind of the same thing happens here. So if you have a convex f, like just skipping over a lot of very important details, but basically like the f being convex is again the easy case. There's provable algorithms, but sort of from the point of view of kind of modeling, this is not nice, because in some sense you can think of a convex function just by virtue of the fact that it has like a unique minimum. You can think of it as a kind of unimodal distribution. Again, cheating a lot, like strongly convex and so on and so forth. But to a first kind of like first cut thinking, you can think of it as sort of looks unimodal. The distributions that we oftentimes want to sample from will more look like something on the right, especially for kind of complex probabilistic models. So they'll have kind of multiple modes. And, in general, this is going to be like a sharply hard task. So kind of like paralleling what's going on with optimization. Again, if you have a convex thing, it's easy to minimize it. Same thing here. If you have a convex thing, it's easy to sample. Okay, so in the worst case, we can't do anything. So maybe let me, since kind of like we're focusing on multimodality here, let me tell you why multimodality specifically is kind of an issue for this for this random walk that I introduced. And that's really not that hard to see, and like kind of the reason that this is kind of troublesome is the same reason that it's kind of hard to go up on a hill, or like when you set the incline too high on the treadmill or elliptical or something, right? If you imagine that the distribution p of x is proportional to e to the minus f of x, and it looks like what the f in question looks like what I have here. So like it has two dips, which is I guess equivalent to p having two kind of peaks. Imagine what's going to happen if I start, let's say, somewhere. Sorry, I guess my laser pointer is lagging a lot. But so here's what's going to happen if you start somewhere around A. Remember what the random walk looks like. So there's a gradient kind of term that pushes you toward, like, kind of down the incline. So it's going to be trying to push you back to A. So if you're hoping to get to this other peak from A, the only thing that you have kind of helping you get out of this, dip is basically like the randomness. And there's ways to formalize this. Like I have a couple of references here from Bovary et al., where you can show that you can easily construct instances where the time to go from A to B can actually be exponential. All right, so how can we try to remedy this? So there's one kind of heuristic that people use in practice quite a bit. It's kind of the analog for sampling, the way that, so it's called simulated tempering, and simulated tempering is to sampling the same way simulated annealing is to optimization. So you're going to somehow try to smooth your landscape and do something that hopefully helps you. So how does this kind of loosely work? Basically, what's going to happen in the case of sampling is you're going to kind of simultaneously try to sample from the distribution at multiple temperatures. So kind of divide this F by multiple different factors, and you're going to occasionally be allowed to swap these kind of like temperatures. I'm not going to formally define the chain because time constraints, but basically you can think of this as sort of like it's kind of like you're running multiple chains in parallel. Occasionally you're allowed to swap kind of particles between the different temperatures. It's not really the chain we're analyzing, but it's a good kind of like maybe intuitive approximation for the sake of the talk. I should say that this is sort of fairly popular in practice and goes back way, way back. However, kind of like theoretical guarantees are very few and far between. All right, so let me tell you a result. So what can you kind of do with this machinery? So here's the setting that I'm going to look at. Suppose the distribution that we're trying to sample from has the following form. So it's a mixture of k shifts of some d-dimensional log-concave distribution. What does this basically mean? It means that this distribution P kind of look like it has k modes, and these k modes sort of have the same shape. It has k modes because a mixture of k distributions. They have the same shape because they're shifts of the same distribution. Again, this is sort of like swiping things under the rug, because when the kind of like components are close to each other, the modes will sort of like merge into each other. But that's like an intuitive way to think of what this distribution would look like. And I guess there's a kind of picture down below. So this is the distribution that we're going to be trying to sample from. I should say that just because if this is the first time you're seeing this setup, you might say, what are you talking about, right? Like, mixtures are easy to sample from. You just like, sample from the, proportionally to the weights in the mixture, then you sample from the component in the mixture. Remember what's the setup here, right? Like, so the setup here is that we have, gradient and or value access to F. So in particular, I have no idea where the means are. I have no idea kind of how to find them. So it's not like I can do this sort of like usual kind of sampling of a mixture that you do when you know what the components are. Okay. And then the result is that basically, if you run this Langevin diffusion process coupled with the simulated tempering chain that sort of swaps between temperatures, you can get an efficient algorithm. So remember, I told you that like in general, you kind of like can't, like Langevin is going to have slow mixing, but it turns out that if you combine it with the simulated tempering kind of idea, you can get an algorithm that runs in time polynomial in all of the, I guess, like, quantities of interest. So in the ambient dimension, in the number of components, and like, in some like 1 over epsilon, where epsilon is some kind of accuracy parameter. And let's say, I guess the version that I'm giving here is where you're trying to sample in the toleration sense. There's, I guess, like other guarantees that we can also give, but for the sake of the talk, I guess let me just like say that. And let me also say that this is a kind of the result is kind of robust in the sense that you can kind of if your distribution is close to such a distribution but not quite equal to it, there's also kind of things you can say. But again, like let me kind of like put that off to the side. Okay, maybe let me pause for about like 15 seconds to see if somebody has questions for the theory. All right. I'm not going to do proofs, but let me give you some sense so you don't feel completely cheated how this works. So again, the idea is basically we're going to leverage the fact that one of the temperatures that we're sampling from is kind of high, so that like, the landscape is sort of flat there. And the idea is that really kind of the following. So I have to somehow convince you that if I start somewhere in the bottom left corner, so somewhere here, I can get to the bottom right corner, like with a reasonably high probability. So how would that happen? So let's kind of do the following thought experiment. Let me think about partitioning, the space for all of these different Markov chains, such that basically like one mode roughly lies in one of the blocks. So how would I get from the bottom left to the bottom right? Well, here's some facts. The walk kind of, suppose that I can guarantee for this blocks the following. Suppose that the walk converges, pretty fast inside each of the blocks. Suppose that the probability mass for each of these blocks is not too small. Then I claim that you can get sort of fast convergence, meaning you can, let's say, you can get fast from the bottom left to the bottom right. So here's kind of how the intuition works. You basically high within each of the modes, so I just only have to worry about getting from the bottom left to the bottom right. How does that happen? Well, these swaps between the temperatures happen with some, like reasonably high probability if you discretize the kind of like the space between the temperatures reasonably finely. Once you get to the high temperature, things are sort of relatively flat, so you can kind of move around this, like this landscape relatively easily. If the blocks don't have too low of a probability, there's a reasonable probability that I'm going to end up in the kind of top right block. And then again, like, I ride the swaps all the way down to the bottom right. Not a proof, but, there's some intuition for why this kind of strategy can possibly work. If you want to know how the proof actually works, like, so basically the main ingredient is some kind of decomposition theorem, which basically kind of tracks the decomposition that I described in words. So basically kind of decompose the Markov chain into two Markov chains, one on sort of like, one inside of the blocks and kind of like an implied projected Markov chain that goes between the blocks. And then you basically prove some kind of bound on what's called the Poincare constant, which you can think of it as some kind of functional analog of a spectral gap that effectively says that, like, if the spectral gap is good inside the blocks and this projected chain also has a good spectral gap, then, like, the entire chain has a good spectral gap. Again, these are sort of buzzwords for any potential experts in the audience, not meant to be, if you don't understand what it is, like, you can look at the paper, basically. Okay, so this is vignette 1. So now let me tell you about vignette 2, and I'll switch gears now a little bit. So now I'm going to be using this Langevin diffusion process as a kind of proof technique. So I'm going to tell you about how you can use Langevin diffusion to prove that you can sort of approximate nice enough distributions by well-conditioned normalizing flows. And this requires a bit of setup, so I'll tell you what normalizing flows are and what this well-conditioning business has to do with anything. Okay, let me set the context again a little bit, the same way I did before. So the context is another very common kind of paradigm with generative models. It's kind of like what I loosely call the push-forward paradigm. So what's the kind of the setup? You want to learn some distribution, given some samples from the distribution, and the parametric form that you're going to fit is going to be the following. It's not going to be like, you're not going to be now fitting the form of the PDF of the distribution. What you're going to be fitting is sort of like a sampler for the distribution. What I mean by that is you're going to be fitting a distribution that you can sample from by drawing a sample from a simple distribution, like a Gaussian, and then you basically push it forward through the parametrized map, so say some neural network G, and then your output is, X is equal to G of Z. I guess if you're a little bit like, savvy with the terminology, but this means that you're fitting push forwards of the Gaussian through like a, through maps parameterized by a neural net. Now, I'm sure by far most of you, like, there's kind of multiple, I guess, instantiations of this paradigm, but I'm sure most of you are familiar with GANs. So maybe I'll just like briefly recall that, just so that kind of like it helps you, I guess, like map to things that you know. So in GAN world, what I described, so this push forward is just a generator. So you parameterize a generator, and then you simultaneously also train a discriminator, which is also a neural net, that's trying to kind of distinguish whether the sample generated by the generator are kind of like, similar or dissimilar from the, like from the training data. And then you train this as some kind of adversarial game where the generator is kind of trying to, generate images that are kind of capable of, I guess, like confusing the discriminator, and the discriminator is, trying its best to discriminate between the, two types of samples. So that's GANs. Normalizing flows were in some sense kind of introduced, or at least like gain popularity if not introduced, as kind of like, resolving some of the shortcomings of GANs. And to tell you sort of like what they are and what the motivation is, maybe let me kind of tell you what are some of the pros and cons on GANs, because then it'll be easier for me to tell you how they're resolving some of the, or how they're trying to resolve some of the issues with GANs. So on the pro side for GANs, what you have is like, they're basically the first, I guess, like family of models that were capable of generating images that are, very photorealistic. And that's even possible with relatively kind of small models. So you can train a GAN of a relatively moderate size that generates like, relatively good images of faces. They're also easy to sample from. That's basically how you parameterize them, right? Like you parameterize them by, having an efficient sampling mechanism. what's on the con side? They're like a devil to train, basically. So the problem that you're trying to solve when you're training them is a kind of min-max optimization problem. It's some kind of like, or you can think of it as a saddle point optimization problem. And typically the optimization is much more tricky to get right than it is for, standard non-convex minimization problems. In particular, some of the issues that plague them, maybe like the most prominent one is something called mode collapse, which is kind of what I have illustrated on this picture down below. So if you imagine that you have some kind of like a distribution like this one that I'm hovering over, so some distribution that looks like it has kind of mass on a couple of separated modes, what happens oftentimes during training is that the model kind of cycles through picking up some of these modes and sort of never really picks up all of them together. So that's a kind of pretty prominent training issue. And on the side of evaluation, they don't come with the likelihood. So the way that I parameterize the problem, it's not exactly clear how to write down a probability density function. So you can't really train with maximum likelihood, which is the first, the reason maybe like in the beginning why people started training with these kind of adversarial, sort of training where you have like a discriminator that's trying to tell you how good the generator is. Okay, so normalizing flows are going to try to basically resolve the issues on the side of cons. And the idea is actually kind of exceedingly simple. So you're still going to be training a push forward of a Gaussian, let's say, and you're still going to be parameterizing the push forward by, let's say, a neural net. The only change you're going to make is you're going to make the generator be invertible. Okay, how does this help? Well, if I have the push forward of an invertible map, I can now write a PDF. Like if I want to write down the PDF under this distribution at a point X, it's basically the density of the Gaussian at the pre-image multiplied by some kind of like, change of volume factor, which is basically the kind of like the determinant of the Jacobian evaluated at the appropriate point. And okay, now that I have a likelihood, I can basically do gradient descent and, all is good, or maybe all is good, right? Like now I have a likelihood, I can maybe evaluate the model. I don't have to do adversarial training. I can do gradient descent. Tiny issue. So the tiny issue is that even though, I've written down a formula, the determinant of a, D by D matrix will generally take me D cubed time to compute. Maybe a little bit more efficient if you have kind of efficient matrix multiplication, but basically like it's going to be an inefficient operation if D is humongous, like, if I'm training on images. So I will want to restrict the class for G somewhat so that this determinant, I guess, like operation is somewhat cheaper. Okay, so to make this somewhat cheaper, again, there's multiple sort of things you could do here, but probably the most popular way to do this is what I called affine coupling normalizing flows. And the idea is that you're going to try to make the Jacobian be triangular. If I have a triangular matrix, the determinant of that matrix is just the product of the entries of the diagonal. That's a linear time operation, so I don't have to pay D cubed. So at least I've gotten I've gotten rid of that particular kind of computational bind. So what are these affine coupling flows? Here's kind of how you parameterize them. So you basically, it's it's deep learning, right? Like, so you're gonna kind of stack multiple transformations of a particular type. So what is the elementary transformation that you're stacking? It's this kind of transformation. So if I have a vector x and I'm trying to transform it to a vector z, what I'm going to do is the following. I'm going to take one half of the coordinates and let's say fix them. So I'm going to take the output at the first half of the coordinates to be the same as the input. So I'm just copying that part. And for the other part, I'm going to take this kind of operation. So basically, I'm going to take the second half of the coordinate, entry-wise producted. So this O dot notation means entry-wise product with some parameterized nonlinear map of the first half. So like of the x's from 1 through d over 2, and then maybe add some affine, maybe adds like some shift or something that's again parameterized and is also just a function of the first half of the coordinates. Okay, it's not super kind of important that you sort of fully, I guess, track what the form of the transformation is. What's important is that one half of the coordinates gets kind of copied, and the transformation has this kind of decoupled form where what you do is even the parts of the coordinates that do change, what you do is like you take the kind of the other half and you just kind of entry-wise product it, and that's the only way that things kind of interact. And if you sit down and do a little bit of kind of elementary calculus, what you're going to see is that the Jacobian for this kind of transformation is indeed lower triangular, which means that you can efficiently calculate the determinant, which kind of is what we were trying to do. Okay, that's affine coupling flows. How good are they? Well, let me show you some I guess like samples, and this is stolen from the OpenAI website for the model. You can see that there, like I guess it depends how many of these you've seen before, how surprising it is or not, but they're kind of comparable quality to the things I've been showing you from GANs. And this was like maybe one of the first times where people kind of like got a likelihood-based model to generate kind of like samples that at least to like, to the eye look sort of similar to what you can get from GANs. Okay, so now how are we doing with the side of pros and cons? So I described to you what kind of what the pros and cons of GANs were. I told you what flow models do. So how are we doing with pros and cons? Okay, it turns out that on the pro side, what you keep is photorealism and efficient sampling. Training is stay blur. So I put in the like kind of in brackets, because what happens is that now you've changed your problem to like a likelihood minimization. So it's just like a minimization problem. So it kind of evaluation is also easier. So that kind of resolves some of the issues with GANs. But there's no free lunch. So on the con side, what the problem is with these models is that they are humongous. So basically, in practice, if you want to get a kind of normalizing flow that generates samples kind of comparable to the samples that I showed you on the previous slide, the model needs to be extremely large. In fact, the model that I showed you on the previous slide is something like 1,200 layers deep, and train time is something like about 40 GPUs for about running for about a week. What that means is that if you're like an independent researcher, not in one of these big companies, you're unlikely to be able to train a good enough flow model. So there's another very, very kind of like important con, which sort of like which is going to be the focus of the next couple of slides, which is that which is also the reason why I said the training is stay blur but not stable, which is that okay, the log likelihood had this term, the determinant of the Jacobian. So if your Jacobian ends up being kind of close to singular, so if it ends up having very small eigenvalues, the determinant is going to end up being close to 0, and then your objective blows up. And this is a non-trivial kind of problem in practice. This is like a very, very common problem. And what I'm going to try to tell you is kind of like where this is coming from and sort of like when you could possibly fix it. Okay, so the pitfall for this section is, can affine couplings be well conditioned? And maybe like just to expand on it a little bit, which distributions can you represent by well conditioned affine coupling flows? So let me kind of tell you the story a little before I tell you the result, what the story was a little bit here, because there's some obvious questions that you might ask. So on the side of theory, what happened was that kind of around the 2020s, like several papers simultaneously proved universal approximation via these affine coupling flows. But there was a very kind of interesting aspect of these constructions, which is that all of the constructions were poorly conditioned. What that means is that if you wanted to get so in any kind of universal approximation result, there's some kind of accuracy parameter epsilon, and then what you are effectively trying to say is if I want like an epsilon approximation of the distribution, how large does the network need to be as a function of epsilon? That's kind of how usually universal approximation results kind of sound. So an additional aspect of all of these constructions was that as you let the accuracy go to 0, the conditioning also worsened. So basically, there's some kind of poly 1 over epsilon dependence that said that if you want a very accurate approximation, then the conditioning of the model also blows up. So the important thing is that this kind of feature of the constructions happened no matter how nice the underlying distribution is. So the reason why I'm underlining this is that you might just say the following question, right? Like you can say, well, okay, I'm trying to fit an invertible map on images. Images are maybe kind of inherently lower dimensional. So why are you surprised that the Jacobian will be close to singular? It's like a kind of low dimensional manifold, and you're trying to write a full, that you're trying to write as the push forward of a full dimensional manifold. The point is that even for kind of nice full dimensional distributions, all of these constructions kind of had this problem. And in fact, we had plenty of kind of synthetic simulations where if you try to fit like a kind of in this paper with Fred Koller and Raj Mehta, where even if you try to fit it on a kind of nice fully dimensional distribution, it still was the case that the kind of normalizing flow was kind of ill-conditioned and had suffered from this problem of kind of the condition number blowing up. So what this means is that somehow this indicates that maybe this is a consequence not solely of the fact that you're trying to fit low dimensional data, but also somehow of the restriction that you're getting by kind of the shape of the affine coupling. So then the next question you might want to ask is like, okay, can we kind of derive some sort of universal approximation result for any kind of reasonably nice family of distributions that doesn't suffer this kind of poor behavior of the conditioning? So that's indeed what we showed in this paper with Holden Lee, Chirag Babaraju, and Anish Sevakari. So we basically showed that if you have a log-concave distribution with condition number kappa, you can approximate it with a normalizing flow that has condition number that's kind of poly in kappa. Just to expand a little bit, like what do I mean by the distribution has condition number kappa? I mean that the Hessian is kind of squeezed between, let's say, identity and kappa times identity. There's another caveat here, which is that the way that we're doing is with something called like a lifting. So in fact, what you do is you take your underlying distribution, you pad it with Gaussians, padded meaning that you add extra coordinates that are just independent Gaussians, and that's the distribution you try to approximate. We didn't come up with this kind of like out of thin air. We actually saw in a previous paper with Viraj and Fred that actually this is sort of like this helps in practice. So this kind of padding actually helps in practice. This kind of theorem gave us some, I guess, theoretical explanation for why this is the case. Okay, so now what's kind of, as I said before, like universal approximation results usually have some kind of like, flavor that for every target accuracy epsilon, there's, like some model that epsilon approximates the distribution. Basically, that's how this theorem says, with the caveat that the condition number doesn't get worse. So basically, the way that the kind of formal theorem sounds is that it says for every kind of accuracy parameter epsilon, you can find some affine coupling normalizing flow such that it epsilon approximate the log-concave distribution in question, and has some size that depends on epsilon. And more importantly, if you look at the Jacobian at any point and kind of any direction, it's going to be bounded between some poly and kappa. I guess what I'm just saying in math is that the condition number at any point of the Jacobian is bounded by poly and kappa. So that's the result. What does this have to do with Langevin dynamics? Here is actually a very nice connection. The way that this proof works is as follows. Basically, the way that you get this affine coupling flow is by simulating with an affine coupling underdamped Langevin dynamics. So underdamped Langevin dynamics are kind of a form of Langevin dynamics, which has a momentum term. So you can think of underdamped Langevin dynamics kind of being to Langevin dynamics as like, momentum methods are to standard gradient descent. So as you can see here, there's some like, position variable xt and also some velocity parameter vt, and then kind of you update them as kind of these two formulas here. And again, if you look at them, it kind of looks very reminiscent to how kind of the updates look for momentum-based methods. If you stare at this for a little bit, you can see that the form of these updates kind of looks like the affine coupling form. So xt gets updated with vt, vt gets updated like, with kind of xt separately. So they're sort of decoupled, except for the fact that there's this like, Brownian motion term. So this is not like it's a stochastic kind of like, it's like a stochastic update, not a deterministic update like it is in an affine coupling. But intuitively, this is why this is convenient, like starting with Langevin dynamics. It's because you can kind of like think of the xt and vt as the two blocks of variables in an affine coupling. So the reason that okay, so there's another kind of important.
So Andrej, yeah. If you could wrap up in the next 2 minutes, that would be perfect.
Definitely. So there's another kind of important ingredient that you need, which is that because this is a stochastic map, you can kind of write down a deterministic version of this map, which introduces some interaction between the xt's and vt's. And it turns out that you can kind of like approximate this alternate deterministic version with something called Hennen maps, which are kind of important maps and which play like some central role in what's called the symplectomorphic diffeomorphisms. Basically, the main kind of proof ingredient is to prove that Langevin dynamics is well conditioned, meaning that if you look at the kind of the push forward at any time, like if you look at kind of the flow of xt and vt up to any point t, essentially like what you end up with is kind of like is a well conditioned map to any like up to any time t. Okay, so let me maybe then go to the very end. I'll skip the last vignette in the interest of time, but basically let me just leave you with the final slide, which is that I think this is like a kind of very exciting area for theory. So there's kind of like a lot of variety in terms of generative models nowadays that you can use, and it's sort of not clear how to how to tease out what exactly are the relative pros and cons, and I think theory can help here. And yeah, let me stop here. 2 minutes, right?
Yes. Thank you, Andrej. This was great. So we have time for one quick question. So if you want to ask a question, you can just unmute yourself and ask it. Okay, so I will just use actually Daniel's question because I also was wondering. So when you were talking about this theorem for this, like, essentially case-shifted distribution, like how important it was that was exactly the same distribution shifted? Like what really you leveraged in the end there in this proof?
Yeah, it was very fast, so that's why like that goes. So basically, if you remember, one of the decomposition theorems effectively needs that the blocks that you get for each of the temperatures don't have too small of a mass. If you have sort of like lopsided, in terms of volume parts of the mixture, they can get exponentially kind of poorly distorted as you go up in temperature. And in fact, there's like a lower bound. Basically, there's some kind of query theoretic type lower bound that says that if even if you have mixtures of Gaussians which are more than like 1+1/d or something covariance matrices away from each other, in fact there's like an exponential lower bound on the query kind of complexity that you need to get a good approximation for the sampler.
I see. Thank you. So this is kind of, well, not all the exactly condition number, but some kind of just non-degeneracy condition. So that's very nice. Okay, we are at the top of the hour. I actually have more questions, but I guess maybe I will send you an email. So anyway, thank you so much, Andrej, and thank you everyone. And essentially, we will have a fourth and last session of this workshop in the afternoon.